Well, welcome everyone to today's Research Pays Off. My name is Lauren Dow. I'm the Communications Coordinator for the National Road Research Alliance and for the Office of Materials and Road Research at MnDOT. Today we have a great presentation lined up. First, I want to let you know that next month, for January of 2021, we will be taking the month off due to TRB being shifted to a virtual experience over the course of many days and weeks. We felt like it might be easier for everyone if you had the opportunity to pay attention to TRB, and we would just take the month off. But in February and beyond for 2021, we will have more presenters scheduled, and you can watch for that information coming soon. Today's session is being recorded and will be available on our YouTube channel by the end of the week. You can find all of our previous webinars there in a Research Pays Off playlist. You can just search for the National Road Research Alliance on YouTube, and you should be able to find us pretty easily. Just a quick reminder to please keep yourself muted during the presentation. We plan to have a time at the end where we can go over some questions. You're welcome to write in your questions into the conversation box as you think of them throughout the presentation, and we'll come back and address them. At the end, you may also unmute yourself to ask your question if you would prefer. Today we have MnDOT Research Operations Engineer Bernard Izevbekhai from MnDOT. He works in both concrete research and geotechnics research pretty simultaneously, and today he's going to be speaking about the evaluation of performance of MnDOT unbounded overlay using reliability analysis. And Bernard has many years of experience in a variety of areas of pavement and transportation related research and academics as well, so we welcome him today to do this presentation.
Thank you, Lauren. Well, we have approximately 50 minutes for me to do my spiel, I would say, on Minnesota's unbonded concrete overlay performance. And as we go on in the presentation, I would gradually define the various words of the topic: reliability analysis, Minnesota's unbonded concrete overlay performance. Each of them will be defined, and that will be mainly what the presentation will be about. It might appear to be a little bit didactic, and that's because of the nature of the mathematical methods that were used. And one of the things about our approach in our evaluation of performance of various fixes in the network is that we want to use methods that are tenable, particularly as the freeways have reached a point where we can actually define performance of certain fixes. So just come along with me. The first thing I want to do is lay a foundation that we do have a mechanistic empirical design program for unbonded overlay. That's not what this presentation is about, but these are tied together. Somebody once opined at the National Academies that gradually there should be a discussion between the design processes and the performance evaluation. One should feed the other. It should be a kind of cyclic process, a symbiotic process. And that's why I just mentioned this. There is a design process from a pooled fund which completed very, very recently. I'd like to salute my co-authors. The first is Norma Farrar, who was my student worker paraprofessional for a couple years. But just like most people do, she has found greener pastures. And I also want to salute our office director, Glenn Engstrom, who is a co-author. He had the passion for us to do the kind of analysis that led to this paper. This paper was published by the National Academies. It was published this year in the transportation research record, and that's the link. You can get that. You can access that paper either from Google Scholar or from anywhere. It's a published paper. So this presentation actually stems from this paper, which was published by the National Academies earlier this year. So today we will look a little bit at network asset implications. Why is unbounded overlay an important element in our network pavements, in our network of pavements? And we will do some definitions and characteristics of unbounded overlay. What is unbounded overlay? Why should we even be talking about it? And we will look at the performance curves, how the ride quality changes over time. And then we will do some analysis of those curves and see the kind of things we did in order to improve what the model in our pavement management program. We looked at it and we requested for a refining of the model, came up with model constants that can be used in the sigmoidal curve, which is built in our pavement management program, or we came up with a simpler performance curve, a simpler model that has two model constants. The sigmoidal curve actually has 4. And we also discussed the predictive variables. I mean, what are the kind of predictors that we have for remaining service life? And remaining service life, we define our remaining service life as 0 when the ride quality index reaches 2.5. Our ride quality index is it's a proxy for ride. It's the reverse direction. For IROI increases when the pavement condition degenerates, whereas the the ROQI, which is the ride quality index, which MnDOT uses in our pavement management program, increases with increasing performance. In other words, it decreases with decreasing performance. So we say that when the ride quality index reaches 2.5 or has degenerated to 2.5, we have a remaining service life of 0. So that definition is very foundational to this paper and to this presentation. Also, we will discuss Weibull analysis. Why would we use Weibull analysis? Why not some other methods? And then we will mention some items in closing. Like I said, we'll say that the remaining service life of our pavement is 0 when the ride quality index is 2.5. That helps us to assign what we will call a remaining service life value to the network of pavements, and it enables planning, because we can say, even though the remaining service life is said to be 0, we know it has some remaining service life. But for the purpose of planning and for the purpose of analysis, we have given that our threshold, so that any analysis we are doing here stems from the time it takes for a particular pavement to get down or to deteriorate to 2.5 as the remaining service life. And that's built into a lot of the formulae that we're going to come across here in a moment. There were certain things we did when we were trying to develop what I would call, in those days, it was a pavement, pavement investment manual. Now it's a pavement investment evaluator. The manual actually did compel us to look into the remaining service lives of all the fixes in the network. And at the end of this presentation, you will see that we actually did that. And unbounded overlay happens to be a microcosm of that large analysis that we did. So there are many health indicators in our network. You know, you have remaining service interval. There's the cost per lane mile. There's the asset value. These are all defined, but time will fail us. There's the asset sustainability ratio. In other words, to what degree are you, by the performance, by the new construction you did this year, how much have you dealt with the natural decline in remaining service life by the new construction or the new activities that were added to the network in a particular year. So the asset sustainability ratio is a great index. And then, of course, there is the remaining service interval. And of course, there is the asset value. One of the things that stemmed out of our analysis was that we said that looking closely at a mix of fixes might be a great idea. And why do we say so? Unbonded overlay, as we will see, is a long-term investment. There are certain investments in the network that are not long-term, but they can move the remaining service life they can increase the remaining service life just by a little investment. Not tremendously, but reasonably. And based on optimization, it's the best at certain times and in certain conditions. But when we mix the long-term fixes and the short-term fixes by an optimized mixture, then we think it helps a great deal. There is a certain analytical method with which I will explain this better as we go along. Now, what is unbonded overlay? We've been talking about unbonded overlay. If you have a pre-existing concrete pavement, there are many things you can do. You can pulverize it. You can do a crack and seat, or you can build a concrete pavement on it. Remember, you already have a real estate right there. So to remove it completely and do a regrade and reconstruction might not be very cost effective. But if you have this existing concrete pavement, there are a few more things you can do. Now I just put a layer there after the concrete pavement. The concrete pavement is the gray. The lower one is your subgrade. Just this is a schematic. And then we're going to build on it. Okay. I have made the joints to be real joints. They're not so because we have aggregate interlock. So you have that interlayer. What is that interlayer? Most people call it a bond breaker, but I hasten to say that it's not a bond breaker. It is a stress relief layer. If you don't have it, you have tremendously high stresses. But if you do, you relieve the stresses. Another thing it does as a stress relief layer, see those micro elephants right there in that tunnel, so-called tunnel of the interlayer. Those micro elephants are showing us the motion of your stress relief layer as you apply the load on it. Now look at that spring system that's happening in the joint. You can see that the rhythm of the rate at which that spring relaxes and compresses is different from the rate at which those elephants bounce up and down. So there is a lag whenever you have these systems, where you have the removal of a load and the response of your structure is not as quick as the rate of removal. You do have some hysteretic effects, and those hysteretic effects can present in very many ways. One of the ways we know, there is something we call Helmholtz resonance, and that Helmholtz resonance is a factor that some people feel as a kind of vibration or as a kind of noise. So the optimization then of the interlayer thickness is important. What you need is a stress relief layer. You don't need a pavement layer right there. So this system works very well, and I will show how there's a relief of stresses when there is an interlayer. Now look at this system very closely. Over and above an existing joint, this is a bit skewed, there is a spike in stress. I mean, if we look at fracture mechanics, the way it happens over a joint, you will have a spike of stresses if that's the joint that is being overlaid. But if you introduce the interlayer, then you see that green line. that shows the attenuation of stresses. So the interlayer is a stress relief layer. It reduces stress concentration and makes it, just say that it has a cushion effect on the existing pavement. With the reduction of such stresses, then there is longevity. No wonder unbonded overlay lasts very long. If you didn't have that stress relief layer, what will happen is that those tremendously high stresses will cause very early degradation, and it will compromise the service life. So the stress relief layer is a very vital aspect of unbonded overlays. That's the reason why when people call it bond breaker, I say, no, it's not a bond breaker. It is a stress relief layer. To validate the fact that stress relief does occur, we did an experiment at MnROAD. We used fiber optics for the first time in 2013. And we put some fiber optics cells on cell 140 and cell 240, contiguous cells, where we had a thin unbonded overlay, 3 inches. What we found out was very impressive, because hitherto we all assumed that stress relief layer causes stress relief. Nobody ever really validated it. There must have been some work done by Kazanovic, and there was a little bit of an inroad into this by Alexandra and I some years ago. Alexandra Akari and I, we did some work some years ago where we showed that there was some stress relief. Then we used the vibrating wire sensors. And so we showed that there was an attenuation of stresses, but we didn't really validate it, and we didn't go out to present it or anything. But in this, you can see, we had the embedment sensors, you have the longitudinal sensors and the transverse sensors. And on the left-hand side of this table, you see cell 140, and on the right-hand side, you see cell 240. If you compare column 2 with column 5, and just keep going, you will see that at all times, the stresses or the strain, I beg your pardon, in cell 240 was always less than the strain in cell 140. Now, cell 240 had a thicker interlayer. We were trying to investigate if we could go down on the thinner interlayer. So the stresses were more reduced with the thicker interlayer than with the thinner interlayer. Now, that has a limit. If we had continued to increase it up to about beyond 3/4 of an inch, then definitely we're introducing another model altogether. And then it's no longer providing the stress relief the way we want it to. So I show the same thing in this curve. Everything that is thick has a corresponding open icon. And you see that at all times, cell 240 had strains that are less than cell 140. Cell 240 had a thicker interlayer than the thinner interlayer. And these were from fiber optic responses in cells, for contiguous cells 140 and 240. I want to talk a little bit about, okay, how did we source our data? Now we've been able to define unbonded overlay. And we have narrowed our analysis to true unbonded overlay. We are not looking at systems where people probably shaved off an asphalt overlay on a concrete pavement and then placed concrete over it and called it unbonded overlay. In that system, I cannot guarantee that you would have stress relief, because most likely you have more than 3/4 of an inch, and then you have a pavement instead of a stress relief layer. So we've narrowed it down to real systems that have interlayers, that have stress relief layers. So what did we do? We went to our network. We looked at 535,000 rows of data from our pavement management. And then from there, we built a software that extracted 15,800 performance curves. And these performance curves had event markers that showed the times of intervention of various other fixes before the unbonded overlay. No, the 15,800 included the unbonded overlay. The unbonded overlay had about 820 825 performance curves of the entire network. Oh, sorry, I beg your pardon, 850 performance curves. And then we did what we will call a stepwise linear regression, and I will explain that as we proceed. Then we perform the Weibull analysis, because we want to know, how does our system behave? How does our unbounded overlay behave? Does it fail early? What is the service life we are getting out of it? And what else? What kind of a window do we have at the beginning within which we can do some preventive maintenance and get this system to even last longer than what we have predicted by the reliability analysis as our expected service life? I did promise that I would talk about this. We did a comparison between the 2013 curve, 2013 remaining service life plot, and the 2002 remaining service life plot. What you see there, boxes 1, 2, and 3, is a split. And the split helps us to explain how we can move our system. Now, you know, it will take more work to move something from box 1, where you have 5 years, 0 to 5 years, or 0 to 10 years remaining service life, to move it to box 3, where you have about 21 to 35 years of remaining service life. It takes a lot of investment. You need something like a true FDR, or for an asphalt pavement, or you better regrade it, or for a concrete pavement, you probably need an unbonded overlay. But it's a huge investment. But if you look at that box 2, that's where we play around when we have most of our systems, where we do rehabilitation. That's where we have a litany of rehab types. We have the diamond grinding, you have the joint resealing, and then, of course, you have the major concrete rehab and the minor concrete rehab. It's in that play box is box 2. So there is a very sensitive area where, with a little investment, you can drive up the overall remaining service life. But the one fix where you can really, in one fix, drive the remaining service life from box 3, from box 1 to box 3, is unbonded overlay, or any other fix that lasts very long. I would say FDR, if FDR in asphalt is built well. Here's a typical plot of ride quality index, a pavement condition index. Ride quality index is in blue. Then SR, surface rating, is a proxy for cracking and all manner of surface distresses that you can see from the surface. So that's the red. But the blue, which we are concerned about today, is the ride quality index. So this is typically, when we did our 15,800 performance curves, we had a bunch of things like this. But we could create a model, because when you see 1,000, 15,000, almost 16,000 of this kind, and then you split them into the various fixes, then we can create a performance model. And that was the next thing that happened here. You know, I've played with performance models, and I've been able to come up with the fact that one way to look at it, just from elementary calculus, the zone where you can do preventive maintenance, at that zone, your change in your rate of change of your RQI with respect to time is very small. It tends to 0. So we can use that to determine the area where we can do preventive maintenance. Your maintenance is not preventive when you're already dealing with real distresses, but you do preventive maintenance when the system is still good enough for you to maybe just seal the joints or something like that, or do a little bit of diamond grinding. And then it pays off because it projects that performance curve down the road many years. But if you follow that performance curve to your right, you get to a point of inflection. And at the point of inflection, your second derivative of your performance curve tends to 0. And that's a point of inflection. I say that at that time you are already changing your rehab to something less aggressive into something more aggressive. And below that, where you see that the rate of change of your performance curve with respect to time is significant, it mathematically, I would say, tends to infinity. That's the point where you do a regrade. That's where you do a reconstruction. And possibly that's where you would do an unbonded overlay. Now let's look at the performance curve schematically again. There are certain indices that we have defined. When you do an intervention in the network, there's usually a spike in the RQI. Thankfully, we made RQI to be the higher the better. So there's usually, so you can see the RQI underscore spike. That shows the spike. Now, we're trying to find out what predictors we can have for remaining service life. What are these things that can indicate that you have a good remaining service life for a particular fix? And then there is the time to rehab, TTR. That is the time from the initial construction to the point at which we did our unbonded overlay or did whatever fix we are looking into. And again, we have what we call TTR-MR, which is the most recent time to the time since the most recent rehab. You will see how significant that is later when we begin to wonder which of these variables were significant. Another thing to look at is the sigmoidal curves, which the pavement management, our pavement management uses. There are 4 different indices, 4 different model constants. You can see RQI is Q minus e to the power a minus b operating on c to the power t, where t is log of 1 over age, where age is in years. You know, pretty complex formula. However, here you see 4 model constants. So we thought of an improved model constant where you have 2 indices. That z you see there, z is the initial condition after your rehab. So z can be a good predictor. And then you have an exponential decay that would occur later, which is typical of any performance curve, where you have our capital B, which is the next e to the power bt. So that's a much simpler model, and we will see how this worked for us. We did propose an improvement of the model constants, even though we said they are quite complex when you start dealing with 4 model constants. There was a current, and then we proposed that after doing our rigorous analysis. And then we looked at how the curves approximated to a Weibull number. Now, the Weibull value for remaining service life, we will talk about that towards the end of the presentation. That was one thing that constrained us. It's very hard for us not to mention Weibull now, but we will deal with it towards the end of this presentation. And then we have a sigmoidal model, and then we have our simplified model, and we have our model constants. So one thing we did in order to evaluate how close these are to our simplified model, we used what we call the Kullback-Leibler Divergence method. I didn't go into the arithmetic of this, but they are in various papers I can share with individuals who want to know how to do the Kullback-Leibler. These are ways of comparing curves. You can't use statistical methods. You have to use these divergence methods. And you can see when we have the improved model, our KL was 0.6, which means the divergence from between the 2 curves was 0.6. Whereas for the previous model, the divergence was 7.4. Mathematically, that's a tremendously huge divergence compared to how we did the improved model. And now we will say that if somebody uses our simplified model, the work is less rigorous. You approximate to the sigmoidal model because you have a very small divergence. The Frechet distance method of measuring divergence is another method, but it's more rigorous. So the Kullback-Leibler, I would recommend that to anybody. So we had a performance the sigmoidal model, when we improved the model, it gave us 35.5 years. And then the 2-parameter sigmoidal model gave us 35.8 years. Now back to our prediction variables. We wanted to say, instead of measuring remaining service life, what can we just do? What can we do? Can we find some other indices, some other variables that we can just, that are easier to measure, that are easier to decipher and use them? So we looked at what I had talked about before, the starting variables, time to initial rehab, time from the most recent rehab, condition at rehab, condition of the surface rating at rehab, then the spike. We looked at that. So we fed them into a statistical program called Statistics. It ends with an X. And we did what we call the stepwise regression analysis. I want to tell you why we do stepwise regression analysis. If you have very many variables, very many independent variables, your model is likely to be good just because there are many. And another thing about the fact good in the sense that your R squared is high, right? But R squared, you can have a very good R squared for the temperature variation in Minnesota and the rate at which birds flap their wings in Guatemala. It doesn't mean anything. You can have very good R squared. However, your adjusted R squared, which formula is shown in the third bullet there, will not improve when you add an insignificant variable to your model. It will only improve if that variable is significant. And that's why we use the stepwise regression method. So the stepwise regression method goes through a lot of combinations of the dependent variables with the independent variables. Like if you have 6, it will choose 6 combination 6, 6 combination 5, 6 combination, that large number, and work the models and see what kind of a model you have. But the stepwise regression just goes through that in a moment and gives you the surviving, gives you the model that has the surviving independent variables with the dependent variables, and maximizes the number and has the, so you have the maximum number of independent variables with the dependent variables, with the dependent variable. So that's what the stepwise regression analysis did. And the result we got from that stepwise regression analysis was that the time from the most recent rehab was significant. Now, the others, I dropped them. Not that I dropped them, the regression process dropped them, because the p-value which we got there was higher than 0.05. That was our threshold. So with the p-value much higher than 0.05, we say, well, that's not significant. But again, if somebody had chosen a p-value of 0.1, some of them may be significant. And the ones that came close are the CAR RQI. That's the condition at rehab. That came close, but it didn't make it with a 0.05 significance. I just want to mention that there is a reason why the time to rehab, since the most recent rehab, is significant. The reason is this: if you improve your system, the Markov's chain, if you do a Markovian analysis, it says that it's a memoryless process. In other words, it doesn't remember what happened prior to your immediate analysis. Now, that Markov process, the Markovian assumption, is very strong. What this model is telling us here is that the Markovian assumption works with unbonded overlay. After you've done very many things over the years, that what you can use as a predictor is the time since your very last intervention, not the time since you did your original construction. So that validates the Markovian assumption, which we didn't help the process. It just gave us that answer, and we found that to be real. Now, I want to talk briefly about the Weibull analysis, which we did. The reason why we do Weibull analysis is that it gives us not just a stochastic analysis. It's not, for all intents and purposes, a deterministic analysis, but it is highly probabilistic. And it's based on probabilities, but it has strong features, which I would explain. Now, the features include the fact that Weibull analysis gives you your dream and gives you the interpretation. Weibull analysis does not assume that you have a normal distribution. It tells you what kind of distribution you have, and it gives you the three Weibull solutions that we are looking for, which is the maintenance window, the preventive maintenance window, the failure mode, whether it's failing early or failing randomly or it's failing at the end of life. A good design will fail at the end of life. And then also the remaining service life. Now, the Weibull method, why I'm an advocate of the Weibull method is that it started with infrastructure. But when the manufacturers stole it, they held on to it over the years. And now it looks as if we are virtually begging them for us to use it. It belongs to us. We are supposed to use it in our infrastructure because it's highly repeatable. If you do the Weibull analysis, you get the same results in Australia as I'm getting here right now. You get the same results in Nigeria as I'm getting in this analysis. So it's a strong method. And remember, it tells you your dream and the interpretation of your dream. It doesn't just tell you the interpretation of any goofy dream that, that it is told. So it's a very powerful model. It tells you what your distribution is, and it gives you your solutions. No other method does that. So again, the location parameter is very important because we want to know what kind of preventive maintenance window we have. And that's the threshold time to failure. The other method that is of tremendous, the other value that's of tremendous is the scale parameter, which is the characteristic life. We want to know what service life we have, what characteristic life we have. And that's usually the 63.2 percentile life of your system. And then also we need the scale parameter. Very important to know failure mode. There are certain things that you roll out of the shop floor and immediately they start to fail. And then the rate of failure decreases with time. But those are infantile type failure. Those are failures that are occurring early. And then we have the failures that will occur randomly. And those failures will be more or less, when you have a random mode of failure, it's a uniform rate of failure. Paradoxical, So the process we used was to scan all the performance curves and have the remaining service lives projected by those. Then arrange them in increasing order. I said this would be a little bit didactic. And then your CDL, that's the cumulative distribution, CDF, your cumulative distribution function is your FX in that fearsome looking Weibull equation. And then, of course, it's 63.2 percentile. It's an approximate value of the characteristic life, but there's a better way of doing it because we will linearize the Weibull function by taking the log twice and then plot that against the log of time. And then time there is normalized by the threshold time, because we want to see the threshold time of failure actually is the point at which your distribution really seems to begin mathematically. So you normalize that by making the x-axis log of t minus t0. And then we get the shape parameter by getting the slope. And of course, based on the slope, we can now find the remaining service life or the characteristic life by operating on the intercept and the beta, which was the slope. So these are simple mathematical process. You can see here that we don't use probability density function. It's a little bit too complex, but the cumulative density function is shown below. And that is your CDF. Your CDF is the FX that is shown there. So it's normalizing this weird looking function that you get the various solutions, which is mu, the remaining service life, beta, the failure mode, and then T0 is the threshold time, which is your scale parameter. I will skip this slide. So the linearization, in the linearization, we assume certain values of T0. That's one way of doing it. And then the one that gives you the most linear of them is most likely the solution of T0. Otherwise, there is a method of finding T0, which was made popular by some researchers in England. And that method, that value is shown there. So here are some of the results we got. So we did that, and then we found that our 62.3 percentile value is 36.5 years. And then we went further using that scale parameter, using that equation where we consider only the parabolic portion of this curve. Then we were able to find a value for T0 of 7 years. If you look at this, what's the meaning of this? I want to preempt our value of beta by saying that if you have beta that's less than 1, it means your system is failing early. If you have beta that's close to 1, it means that you have random failure, which is uniform rate of failure. Now, the higher your beta is away from 1, the more likely it is an end-of-life failure. And when it's between 1 and 2, it's like a log normal distribution. But when it starts to approach 2.5, you are coming close to the normal distribution. So Weibull doesn't assume any of this. The solution tells you what kind of distribution you have. So we got 1.32 as our Weibull shape parameter, which is the failure mode. This tells us that it's a quasi-random failure, but in the direction of an end-of-life type failure that we had. And then the prediction model also showed 3.58 for service life, which is a validation of what we did with the performance curves. And with a threshold time of failure of 7 years, it tells you that you have a substantial window within which you can do a lot of preventive maintenance and improve your system to even get more than 35 years of remaining service life. I'm going to run through the remaining slides. This is still validation. This is how we plotted the curve, how we normalized it and got our mu. We got our mu in 2 different ways. We got our beta in 2 different ways, and we got our T0 in 2 different ways. So that is one way of cross-checking and making sure we've done the right thing. Now, having said that, I want to say that we did the same analysis for all the fixes in the network. And here, this table shows us the various remaining service life we got. That will be one. The 6th column. The 6th column shows us the failure mode. The 5th column shows us the Weibull life. And we can see that the T0 there actually shows you what kind of windows you have. You can see your unbonded overlay there. We have 7 years as your threshold time of failure. So in closing, I'd like to say that we have actually proven that the remaining service life for unbonded overlay is 36 years. That makes it a very long, that makes it a huge investment. If you weigh it against the cost of unbonded, all you need to do is compare it to a regrade. If you compare it to a regrade, you are saving a lot by doing unbonded overlay. And like every other thing, and then the study also validates the Markovian assumption that the time from the most recent rehab actually is a predictor of remaining service life. We did not distinguish between PASRAC, well, that's permeable asphalt stabilized stress relief course, and the non-woven geofabric. We did not distinguish between them in this research. We just treated the regular interlayers as interlayer, and then we walked along. So that's one of the limitations we have here. So in other words, I'm sure the governing factor will be probably the lower performer of the 2 of them. But well built, they work very well. They provide the required stress relief. We have enough information for somebody to use for pavement investment planning. This is a very good reference. This reference has been very helpful to me in the study of unbonded overlay. You can see that this was a research work that was done by Glenn Armstrong in 1993. So even though they say it's out of print, it's available through Amazon or through anywhere books are sold. You can find it anywhere books are sold. It's a very good reference. Or you can contact me or contact Glenn Armstrong, co-author in this presentation for this work that was done in 1993. Those are foundational things. At the end of the day, you go back to this original work that were done. There's a lot to learn from them. They laid very good foundation in those days. And these are some other references too that will be helpful in looking at unbonded overlay and the stress relief layer. I'd like to acknowledge Nancy Dobenberger, who is our Deputy Commissioner right now. At that time, she was our Division Director. And Sumuvi Hill, who was the Chief Engineer at that time. And Jody Martinson was one of the Division Directors who supported this research and attended some of our presentation in those days. I'm indebted to MnDOT's Dave Janish, who is our Pavement Management Engineer, Kurt Turgeon, our Pavement Manager, and Debarati Gosh, who helped with those with the software that generated those performance curves. Steve Henricks was very helpful in our modification of those performance curves and gave us something that we could use to give to the pavement management unit and say, well, here is what you have. You can use it if you want. And then the district materials engineers were very helpful. We called them time and again, and they gave us good feedback. I acknowledge Jeff Bronner, the MnDOT Research Director, and my colleagues. And I'd like to thank all the NRRA members and everybody who has participated today in this webinar. Thank you for being patient with some of these concepts. They are not very popular, but they are very good. And I can assure you that if we build it right, then we are definitely headed in the right direction. We don't want our pavement to become a fish pond, like you see in that picture. So with that, I always say that the more you look is the less you see. So that's what this slide tells us. I thank you for your time.
Thank you, Bernard. We do have a question here in the chat box. And he apologizes if he missed it earlier. Did you take into account user delay costs in economic considerations?
Yes, user costs in concrete pavement. User costs are of tremendous importance. And we are addressing this in another study, and that's the strength at opening to traffic. We deliberately loaded some concrete pavements early in our MnROAD research facility. We loaded those concrete sequentially early, some were earlier than others, and we're trying to see if there will be short-term or long-term degradation on account of that early loading. So we're trying to shrink the user delay costs that are implicit in concrete paving. We're addressing that in that other study. Another area where unbonded overlay is useful is that you are building on an existing pavement. You're not doing a regrade. So you're not going to cause user delay costs over a long period of time as you would do in a regrade. So your unbonded overlay saves you those user delay costs that would have been implicit in using the regrade or complete reconstruction. Yes, that's a very valid point.
And I have another.
The person who asked that question, I can discuss later the other research we are doing on the strength at opening to traffic if he needs more, if that person needs more information.
Okay. And I do have another one here. The analysis used status X or statistics. Okay.
Yes.
What is the
Yes.
package? Can the work be easily reproduced in R or Excel? Have you explored those alternative methods?
Excel doesn't have stepwise regression analysis. So if you want to do it by yourself, you have to do the various combinations, use the various independent variables. If you have 6 of them, God bless you. You have to do with 4, do with 3, do with 2, and so on. You'll be tired at the end and you will have forgotten which results you got at the beginning. So yeah, statistics has that good advantage. I believe R has the advantage, has the stepwise regression analysis as well.
Okay. And just a reminder, you're welcome to unmute yourself if you would like to ask your question and maybe flesh it out a little easier verbally as opposed to in the chat. But I will read this next one here. Did you analyze the cause failure or complex of causes failure in the model? What means the typical loss failure?
Well, in this, when we were doing the pavement investment manual, when it was a pavement investment manual or a pavement investment guide, we were actually looking at that holistically. And I believe the pavement investment evaluator is looking at that. What this analysis actually looks into is service life, maintenance window, failure mode. That's all this list looks into. But there's a larger, this is a microcosm of a larger study where all those were brought into cognizance. And I believe the pavement investment evaluator still carries that overall goal, which was set at the beginning when it was the pavement investment guide. But this particular analysis that we're talking about today deals with how we got the service life. And our failure has been defined. 2.5 RQI is remaining service life of 0. We are saying that at that point, there's no remaining service life of the pavement. It has failed. Okay. So everything is based on that definition. So it's not even based on even the surface rating, where we would have said, this is what we see. It's based on how it writes, how comfortably it writes, using the right quality index. But don't forget that the right quality index is initially based on a rating that was done by a rating panel, and then we now use the right equipment to have to create a correlation so that we can measure our ride in IROI and then convert to RQI. So this is not the whole gamut. In the whole gamut, then that was those other factors I addressed.
All right,
Hello?
and I have one more question here. And it looks like they felt like that answered their question. Thank you.
Okay.
Did you analyze a concrete overlay using continuously reinforced concrete?
No, we did not. We would like to do that. We would like to work with like Texas DOT or wherever they generally, I know that Texas DOT, they struggled with interlayer at one time because here is one thing with CRCP. CRCP has reinforcement, and then there are some cracks that will occur at a certain interval. That's part of the deployment. You know, now that deployment may be compromised when you use the non-woven geofabric as your interlayer. What we have learned to do in Minnesota, you can beat up the pavement early enough so that the joints will deploy. Yeah, but so at that time, I remember there was a federal highway open house where they did say, well, that they struggle with using CRCP on there. But we will want to analyze their data. I would like to work with Texas DOT, capture their data and see what kind of performance life they are getting. But I know that they did struggle with the non-woven geofabric. But that's not to say that they will not use something like PASRAC or some other interlayer. So it is something we have in mind. But what we have here is jointed, plain, doweled concrete pavement. That's what we have in Minnesota. It's not continuously reinforced. So this analysis does not include continuously reinforced overlay. Neither does it include the overlay on CROCP. But if we are doing this over on CROCP, that's having a bonded overlay, an unbonded overlay with jointed pavement on a CROCP. But we'll have less trouble with that because you have less of those joints, which we are trying to reduce the stresses by using the interlayer when we use CROCP. I'm sure the performance will be better. If we put a jointed plane on a CROCP, the performance will be better. But if you want to use a CROCP on a CROCP, we need to analyze that. And I can work with Texas DOT to find out how that works.
Okay, thank you. The last question I see just is asking about the recording, and the recording will be available on our YouTube channel. I should be able to get that up by the end of the week. And you can search for the National Road Research Alliance on YouTube, and you should be able to find our channel with all of our recorded research pays off sessions and a number of other videos and webinars that we have recorded. And I want to just remind you all, since we are just about at the end, if anyone has any other questions, you can feel free to ask them either in the chat or over the audio. And as anyone might be preparing those final questions, I just want to say that our next meeting will be in February, and we will be using Microsoft Teams for that. MnDOT is transitioning fully over to Microsoft Teams and is phasing out Skype. So this is one of our last sessions to be using Skype forever. So hopefully that will provide a little bit of a better technology experience for everyone as well. Okay, well, I think we're all done. I think that's all the questions. Thank you very much, Bernard, for all of that great information. And thank you to everyone for joining us. Hope you have safe and happy holidays.